Okay, so in this video, we're going to tackle the nuts and bolts of linking theory to practice, which is in fact at the heart of what we do in engineering education. Now, if you watched the previous video, you might get some ideas from this one on how better to connect or work between the different kinds of knowledge structures that you've identified in your particular subject area. So I'm going to be introducing you to a very simple tool, one that has been used globally across many different fields. And what this tool does is it helps us not only to differentiate theory and practice, but to determine what the steps are between the theoretical and practical, or the abstract and concrete elements of the areas in which we teach. The tool has been widely used across the faculty, and I'm going to be supporting what I'm talking to you about using case studies and examples from work that's already been done in the faculty. So, cumulative learning is an educational principle, and it's the ability to build on and integrate past knowledge as opposed to its opposite, which is segmented learning. And segmented learning is where students learn a series of ideas or skills that are strongly tied to their context of acquisition, making transfer and knowledge building problematic. In other words, segmented learning is like siloed learning when we talk about the siloed curriculum. The basic premise of all learning is that it happens when we know why we are doing something, what, in other words, and how to do it. Cumulative learning leads to the ability to connect the dots, to make the link between theory and practice, between principles and procedures. Now, a very simple educational tool, which has been used extensively, is called the semantic wave. What it helps us to do is not only differentiate between theory and practice, or the abstract and concrete, but actually all the steps between these poles. If our role as educators is to facilitate learning, then learning happens when students connect the dots between the poles. Now, here's a slide from a previous workshop which attempts to visualize the steps between an abstract concept and a context-specific application. I'm going to be showing you many more examples in our own context. The point is, firstly, there are many different ways to calibrate your scale. In other words, that scale on the right, there are different versions of that, because it does depend on your parameters. But secondly, that our role is to enable our students to move up and down the scale in wave-like form over time. Now, what does this look like? There are many different examples of waves. Here are examples of unsuccessful waves. So these two things are called flat lines. You have a high flat line or a low flat line. So this is when you see students, for example, reproducing theory or abstract answers to a set question without any application to or unpacking in relation, let's say, to a problem or a context. In other words, where we might not really see if they understand the principle of a concept and how to potentially apply it. Alternatively, a low flat line is where students are given a very context-dependent problem in detail, often very in common sense terms or very practical, and they're not required to draw on the theory or the principled knowledge that they may have been taught or acquired, which could challenge their understanding of the context. In other words, flat lines represent a lack of transformation or reinterpretation of knowledge in relation to a task or an assignment. Now, here's another example: escalators. Escalators, we see this in the school syllabus all the time, or in school teaching very often. These are down escalators, and essentially this is a list. A concept or an abstract principle is introduced, for example, in technical or formal terms, and then it's simplified and applied to a problem and discussed in more detail. The escalator breaks off, and the lecturer simply moves to the next concept, and so on. Even if these are later all drawn together in an example or problem-solving task, if there have been too many broken off escalators up to that point in time, you will see that students are unable to connect the dots, that they can't necessarily make the upward movement to connect concepts together in and through application. In other words, they can't do what we really want them to do, and that is to weave it all together, building cumulatively over time, such as in this example of a fairly standard or ideal semantic wave. Now let's take a look at examples in the faculty. Let's take a look at some of the examples of how different staff members across the faculty have actually used the semantic wave to enable cumulative learning in their subject areas. Now, Richard Walls used the concept of semantic gravity to differentiate the artifacts used in his civil engineering module according to their levels of abstraction, from the more conceptual formula to the context-dependent physical buildings and objects. Now, by determining these different levels, he could analyze which of the learning support initiatives he was using reinforced what levels of abstraction and the links between these levels. In other words, he could plot the strategies he used in his teaching throughout his course across the different semantic ranges. Now, this graphic here presents the results of the survey he conducted on which initiatives the students actually found most useful. Now, you'll notice that the highest ranging initiatives all entailed more active physical artifacts. In the third video in the series, you're going to see how he actually approached using these different strategies, particularly the ones that required previously more physical engagement, how he used those during emergency remote teaching last year. Now, taking this differentiating levels and allocating appropriate resources principle further, Lydia Auret applied a semantic range analysis to process control. Now, her levels range from abstract concepts, such as mass and energy balances, as well as those principles, abstract principles, entailed in control theory. Starting there, we see a movement through mathematics and into the control environment, which she's labeled as levels 1, 2, 3, 4, and 5. Now, just as an aside, those of you who watched the knowledge video will recognize, both in the previous as well as in this example, the movement from strong natural science-based hierarchical knowledge through strong horizontally structured mathematics to the weaker knowledge structure in terms of programming. Now, these differences, remember, determine how much time is actually spent on acquiring and using that particular form of knowledge appropriately. Now, the original structure of the module, as in many of our cases, was lecture, tut, prac for 10 weeks, then a plant-wide control design project during the last 3 weeks. Now, in previous iterations of this course, what Lydia had picked up was that students weren't able to connect the dots between the different concepts and application covered during class. So she restructured the curriculum, introducing that final project right at the beginning and linking each week's concept and application to elements in the project. She scaffolded mini assignments towards the whole project over the entire period. The assignments start out at a more concrete level of abstraction with a narrow range and progressively span a wider range until the final assignment covers all 5 levels of abstraction. Now, each new assignment represented an increase in complexity and a wider range of levels of abstraction. We've many more examples in the faculty, and I'm just going to point out a few key features that are relevant in planning for hybrid emergency remote teaching, learning and assessment. Corné Coetzee analyzed which initiatives in first-year drawings covered which levels and how this impacted on student development of visualization skills. We see here on his little graphic that the facilitated tutorial sessions worked best in pulling the principle through practical application in reference to the real object, we'll take a look at how the absence of physical tutorials was addressed in our next videos. This example from Luzanne Bum and Imke de Kok in Industrial was part of an initiative on encouraging students to pre-read text before the class. In other words, classic flipped classroom, and then assessing their reading using clickers. However, for the purpose of this video, I want to demonstrate their approach to semantic waving, where they actually start this particular class in the student context, drawing on what it is the student knows, the game of Warcraft, and then they gradually weave concepts together by designing a range of peer learning activities, many of which, we'll find out in later videos, actually played out in remote non-contact based environments such as discussion forums. I've uploaded a few of our publications on the application of these concepts, particularly cumulative learning and the semantic wave, to the website, so you're welcome to take a look at those. Finally, in the next few videos, I will continue to refer to some of the principles in this video across a range of case studies and examples, which can hopefully help you to make informed decisions for how you're going to be teaching in the next phase.